So in the central limit here, we're start looking at, instead of just standard deviation, we're going to be looking at standard deviation over root n. So we're looking at samples here, and sample sizes n will change. So we're looking at samples, and the central limit theorem is that if n is large enough, typically greater than 30, but actually it works for under 32. The sample means for a given sample have a distribution that can be approximated by a normal distribution. So we're saying that it's going to be the same as a normal distribution with a mean mu and standard deviation of this guy here. So this becomes our new standard deviation, or we're going to call it standard error of the mean. Standard error of the mean. So just jot that down, standard error of the mean. So our z-score is going to become, this is when we have sample sizes, so just look out for that in the question. Our z-score is going to become x, and they call it x bar in this case, our test statistic, minus mu over sigma, in this case divided by root n. So this is the first video, I think it's number 17 possibly in the statistics playlist, where we're going to look at this sigma over root n. So let's have a look at the first question here. Numerical data for a large population is stored in a database. It has a mean of mu and standard deviation sigma. A computer simulation randomly selects samples. So you're thinking straight away samples, circle it, 400. So we're looking at n is equal to 400. This is done repeatedly. So just rub this out. And from the database, and calculates the mean of each sample. So it selects samples of size 400 and it calculates the mean of each sample. This is done repeatedly until 1200 such means are recorded. So sampling means from a population distribution, and describe the expected distribution of the sampling means. Well, the expected distribution are that the sampling means will be normally distributed. And write in terms of mu and sigma the mean and standard deviation of the sampling distribution of the sample means. So the only information we have here is that n is equal to 400. So we're going to have sigma over root n as the standard error of the mean for these ones. So sigma over square root of 400 is sigma over 20. So that's all we can do in that first question. That's in terms of mu and sigma, the standard deviation of the sampling distribution of the sample means. Okay, question 2, a bit more numbers in question 2. A simple random sample of size 49 is chosen. N equals 49. It's known to be normal. The mean is 9, so the mu is 9, and standard deviation of 2. Find the probability that the sample mean is greater than 10. So we're dealing with samples. So we standard deviation over root n for my standard error of the mean. Standard error of mean, I'll call it just for today. So we're looking at standard deviation. In this case, we're told is 2. So 2 over the square root of 49 is equal to 2 over 7. So our z-score becomes, we're testing 10 against an average of 9, and we're dividing by 2 over 7 in long form. Just do it like this. So we're going to end up with 7 on top times 1 over 2, which you can see is 3.5. So it's going to be way off. Let me just do a quick sketch. I did say I'd sketch all these. So we're testing 10. My average is 9. So you think, well, testing 10 isn't that greater, but let's say 10 is here. My standard deviation in this case is 2. You can see that 10 is on the other side. It looks like it's, well, it doesn't look like it's less than 1 standard deviation away here. But because this is a sample, this is why we use this standard error of the mean. So it's not as simple as just looking at 1 or 2 standard deviations away. So a z-score of 3.5 gives me 0.9989. So 0.011 is left in the tail in here. So the probability of greater than 10 is 0.11% if you want to write it as percentage terms, or you could just leave it as this. Just check what they're asking. Then question 3. Women's heights in Ireland are normally distributed. Mean given by 164.4. standard deviation 6.25, mu 164.4, and standard deviation 6.25. And the source here is given to you: the evolution of adult height in Europe, economics and human biology. And when you go to college and you have to do citations, make sure you do them as you go along and don't leave them till the end. So if a woman is selected at random, find the probability that her height is less than 167. Where is she on this curve? Here's my 164.4. We're testing this girl over here. She's 167. And I have my sigma. And we don't have any random samples or nothing else given to us in this question to start with. So we're testing 167 against 164.4, and we're dividing by 6.25. So that is going to leave 2.6 over 6.25, 0.416. So if I get my z-score of that is my z-score. No, my z-score, I'm just going to get the value between 0.41 and 2, 0.4, and then I have 0.01 and 0.02, 0.416591, and 0.426628. So the big jump between these. The smaller the numbers, the bigger the jump. So what have we got? We're looking for kind of halfway between, actually 60%. If you want to get the exact number here, I'll do the exact number in this video. The difference between these 6591 and 6628 is 0. What's the difference? 28 and 9, 37, 0037. We want to get 60% up. So we multiply that by 0.6. Or maybe just get 10% at 37. We imagine 37, 10% is 3.7 by 6 is 18, and 4.2, 22. Let's say 22 to round it off. So instead of going from 91 all the way up to 28, a jump at 37, I'm just making a jump at 22. So I get 0.6. I'm adding 22, so I'm going to get 13 here. Instead of 91, I'm going to get 6613, or 15 less. Sorry, 15 less than 28. So that's my probability of the woman being, what did we test? 167? 167 against the average of 164. So the probability that she is greater, is it greater? Probability that her height is less than 167 we have. It's equal to 0.6613 to be 100% accurate. Yeah, there's a sample from this question. What's happening? A simple random sample of 25 women is selected. N is equal to 25, so it's a much smaller group, so we have to apply standard error of the mean. Find the probability that the mean height, just missing the end of the end there, that the mean height of the sample is less than 167. So we dealt with 167 before, so we're dealing with the same type of information. 167 minus 164.4, the average, but our sample size, sigma was 2, our sample this case is 25, so we're looking at 2.6 on top divided by 2 over 5, which is 0.4. Just taking a wrong standard deviation, it was 6, wasn't it? 6.25, previous question to 6.25. 6.25 over 5, so we're going to divide 2.6 by 1.25, so just over 2. So that is going to give 2.08. And if we look up 2.08 as a z-score, we get 0.9812, 0.9812. So the probability of less than 167 in this sample of 25 is 0.9812. Explain why you were able to use the central limit theorem in part 2, even though the sample size does not exceed 30. Well, we could say we were able to use the central limit theorem because the underlying population is normally distributed. And actually, it doesn't matter, but in this case, that's how you'd answer this question.